Hello and welcome to GCSE Physics tutorial for topic P6 waves. This is part 3 and looks at lenses and radiation. First of all, lenses. Lenses refract light and change the direction of the light rays. There's two types of lenses. The top diagram shows a convex lens, and that makes the light rays converge or come together. Concave lenses, as shown below, cause light rays to diverge or move apart. When you draw a lens diagram, the principal focus is where the light rays meet, and the focal length is the distance from the centre of the lens and the principal focus. Lenses can produce real and virtual images. It's important you know what this means. A real image is when light from an object forms an image on a screen. A virtual image is when light from an object appears to be coming from a different place. For example, an image produced in a mirror. In a convex lens diagram, you can see that the light rays are converged and the principal focus is in front of the lens. In a concave lens diagram, because the light rays diverge, if you go behind the lens, you can trace back to find the principal focus where the light rays would meet, as shown here. And so the focal length is a distance from here to the centre of the lens. Starting with concave lenses, you need to know how they can produce different images. If you place an object past twice the focal length, so past 2f, and use a concave lens, this will produce a real image on this side. However, it will be inverted or upside down. It will be before 2f on the side past the lens, and it will also be smaller than the object. So this is an example of how a camera works. If you use a concave lens and place the object between 2f and f, as shown here, you create a real image on the other side. However, the image is inverted, so upside down. It's past 2f and it's bigger than the object. So this might be an example of how a projector works, because it makes the object produce an image that's bigger. If the object is closer than the focal length, as shown here, so closer than f, the image produced is actually virtual. It's the right way up, and it's also the same side as the lens, as shown here. It's also bigger than the object. And this is how magnifying glasses work. With concave lenses, the image that you produce is always virtual. It's the right way up, as shown here, but it's smaller than the object and it's also on the same side. So, for example, a peephole when looking through a door. Key questions is to draw lens diagrams for a concave lens and a convex lens. With the convex lens, you would need to show that the principal focus is where the light rays meet, and the distance between that and the centre of the lens is called the focal length. With the concave lens, this time you would work backwards from the diverging rays to where they meet behind the lens, and the distance between that and the centre of the lens is the focal length. Visible light. Light is made of 7 colours of the spectrum. Each colour has a different wavelength, and mixed together, they make white light. Objects absorb some wavelengths of light and reflect others. If you look at an object and it looks white, that's because it reflects all of the light that hits it. If you look at an object and it looks black, it's absorbed all the light. If you look at an object that looks green, as shown here, it's absorbed all of the light apart from the green light which it reflects. Filters are used to absorb different wavelengths so that only certain colours are transmitted. If you look at the diagram here, an orange filter allows all of the colours to be absorbed apart from orange light which is transmitted. You need to know about a practical using a Leslie cube. Before we talk about that, just a little bit more about infrared radiation. All objects absorb and give out infrared radiation. A hot drink that's left out gives out more infrared radiation than it absorbs, so it cools down when left out. A cold drink absorbs more infrared radiation than it emits, so it warms up when it's left out. If an object gives out and absorbs radiation at the same rate, it's at constant temperature. A Leslie cube is a cube that's hollow with different surfaces that can be used to investigate infrared radiation. So the different surfaces might be black, matte white, shiny black, shiny silver. First thing you do is you place the cube on a heat-proof mat. Then you fill it with boiling water and allow the temperature to settle and make sure the temperature is the same for all four surfaces. You would set up an infrared detector as shown about 10 centimetres away from one of the surfaces and record the amount of infrared radiation it detects from that surface, and then repeat with other surfaces. You always need to make sure that you keep the distance of the infrared detector the same from each surface and the temperature that it starts with. What you should find is that most infrared radiation is detected on black matte surfaces and least on shiny silver ones, as shown in the graph below. Radiation. Black bodies absorb all radiation, so none is reflected or transmitted. The intensity of the wavelengths distributed by an object depends on the temperature. So as temperature increases, the intensity of the wavelength emitted increases. But for shorter wavelengths, intensity increases faster, so the peak wavelength decreases. In other words, the hotter the object is, the shorter its peak wavelength. If you pause the tutorial now and try these 3 questions. So, if you had a red filter and you looked at a green bag, it would appear black, but the red strap would look red in a red filter. If you leave a cold can out, because it absorbs more radiation than it emits, the temperature of the can increases and it warms up to the temperature of the room. A perfect black body is an object that absorbs all of the radiation that it hits it so that no radiation is reflected or transmitted. In summary, we've looked at lenses and radiation.